In this video, you're going to learn how we used earthquakes to look deep into the Earth. How deep is the deepest mine on Earth? Is it A. 1 kilometers, B. 2.5 kilometers, C. 4 kilometers, or D. 9 kilometers? It's 4 kilometers. How deep is the deepest hole ever drilled into the Earth? Is it A. 12 kilometers, B. 18 kilometers, C. 22 kilometers, or D. 28 kilometers? It's 12 kilometers. Were you close? The distance to the center of the Earth is about 6,400 kilometers, so the deepest hole is only about 0.2% of the way in. So how do we know so much about the structure of the Earth, since we have quite literally only scratched the surface? You may have seen cutaway diagrams of the Earth like this. So how do we know so much about somewhere we haven't yet been able to explore? We need to use something that will penetrate deep into the Earth and return information back to the surface. The Earth's surface is broken up into several tectonic plates, which are in constant, very slow motion. Earthquakes occur usually at the boundaries of these plates, as they move against each other. Watch our video on plate tectonics. Earthquakes create shock waves, like a bell ringing, known as seismic waves, and these travel both deep into the Earth and around its surface. Two types of seismic waves are made, and each is quite different. P waves. These waves travel the fastest and are called primary waves or pressure waves, as they arrive at a distant location first. These waves compress and stretch the rocks as they spread out. P waves pass easily through both solids like rock and liquids like magma. S waves. These slower waves arrive after the P waves, and so are called secondary waves or shear waves. S waves cause an up and down motion. They travel through solid but not liquid. Earthquakes are daily natural events monitored by seismic detector stations across the globe, which all build up a picture of how the waves travel through the Earth. This is one way of displaying the seismic waves as detected by a seismometer. Notice how the P waves arrives first. And here comes the S wave. It was found that not all of the waves started by an earthquake arrived at the seismic detectors on the other side of the Earth. P waves are detected over most, not all, of the surface of the Earth. The curved paths are caused by refraction of the P waves as they pass through rocks of different densities. Remember, P waves travel through both solid and liquid. The core dramatically alters the path of the waves as they approach or pass through it, which suggests a significant change in density from a solid into a liquid state, magma. This is how we explain the so-called P-wave shadow, and so begin to understand the structure of our Earth. S-waves have a much larger shadow zone, suggesting there is a liquid iron structure deep in the Earth they cannot travel through. Calculations can then be done to deduce the relative sizes of the layers hidden deep inside the Earth and suggest if they are liquid or solid. In conclusion, study of S and P waves led us to the knowledge that the Earth has a layered structure with a solid inner core surrounded by an outer liquid core.